Good afternoon and welcome to Machine Design's webcast. Our topic today is powder metal technologies, designing with innovation to support your unique application and cost requirements, sponsored by Symmco. I'm Jeff Kearns with Machine Design Engineering and Sourcing Group. To begin, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click the yellow Help icon button below the slides. Additionally, we welcome your questions today during the event. We will answer as many as we can during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Bud Jones is an engineer manager at Symmco Incorporated in Sykesville, Pennsylvania, combining more than 30 years of manufacturing experience with dual associate degrees from Penn State in Mechanical Engineering Technologies and Material Engineering Technologies. Bud is dedicated to providing support for complex and difficult component demands. His priorities include research and development of new materials and processes, streamlining new part production timelines, and meeting optimum design properties. Prior to management, Bud has worked in the pressing department, quality assurance department, and process engineering while attaining his college degree. Now let me turn things over to Bud. The floor is yours.
Thank you, Jeff. I appreciate it. And certainly want to thank everyone who's taken the time to log in today. We will try to get to some information here in the text and certainly answer questions as we can at the end. So again, thank you for logging in. I think one of the key things that we want you to get out of this is a return on your time investment. We all have that commitment to our time. It's critically important in a day, and we thank you. And we hope that through these next 30 minutes or so, we get that return to you. I would like to say, though, in these first 10 minutes, we want to provide the information that will help you commit to the entire presentation. We're going to identify technologies that will lead to improvements in your current components, maybe potential new part designs, or even cost reductions, sourcing reductions, stocking and JIT programs, everything that we feel is really dynamic to the powder metal world. But first, who are we? Symmco is definitely an established business here in the United States. We've been producing powdered metal since 1952, and we are truly made in America company. We have one facility here in Sykesville, Pennsylvania. We have about 120 employees, and we are a $25 million company. Different from many in our industry, we are privately held as well. As you will see in the presentation, our customer base is primarily industrial. We are typically a non-automotive company, and we think that gives us the opportunity to use an entire staff to work closely with customers that value service, that do value engineering support, and meeting tight manufacturing timelines. I think one of the keys to any business is looking at someone's mission statement. It's always interesting to see where they want to lie and where they want to head. Our mission statement is pretty simple. We partner with customers that value delivery, service, inventory investment, and custom engineered value solutions. We want to back our mission statement up. It's easy to say something, but here we do have a complete staff dedicated to making that happen. Our customer service team uses every kind of communication today in technology, from whether it's personal contact or out to the EDI-based systems to keep things moving. Our application engineers combine with our engineering team to assist in designs and keep everything timely in quoting or any kind of activity after that you might feel we can do to support you. But I think one of the questions is how. How does powdered metal, if we take a look at the PM101, what can we do? Conversions are easy. That's just a direct machining. Conversions to meet mechanical properties are often used. and productivity increases is quite common in powdered metal. To make a gear, we do hundreds of parts per hour, so it's a very fast system. At the beginning, we're going to ask for 10 minutes to help you decide to give us the entire 45 minutes. And in the next few slides, I'm going to take a few minutes to describe 3 different scenarios that were used to support our specific customers. It could be that it's removing very costly machining. Maybe it's improving materials to gain a mechanical property. Or maybe it is just that simple production rate to provide that on-time delivery. So we're going to take a look at a few different cases here. First of all, gearing, and I think it's probably one of the more typical powdered metal goals. In this case, you have a multi-pound planetary gear system that initially failed all FEA and test requirements of that customer before they considered powder metallurgy. They looked at both machining, different cast operations, but the costs were just too high to begin to launch a very considerable project. Initially, they went to plastic because that plastic could be made at these shapes, certainly a lower cost system. But after they did produce those tests, it absolutely failed. It could not pass the testing they needed. Unfortunately, unless other processes were found, this project was doomed to fail. So what happened is we were able to use our most up-to-date pressing technology and able to produce these parts exactly as you see them with absolutely no machining. The key is, as a industrial-based part supplier, to have this type of complex technology available is relatively rare. The key of combining that press to the tooling to create it, we produced at more than 400 parts per hour, even of those large, most complex. So it was definitely a key to the cost effectiveness. The other item was the material we were able to use surpassed all short-term loads and passed all long-term testing as well. This technology has provided the customer this gear system that they do now offer to their end customers. So it was a program that saved that part. The other thing you look at is converting from fully machined gears. This helical is one of those case studies in particular. The helical was driven by a worm gear, just a standard gearbox. It was definitely a proven box, used for quite a while, but as all things, cost reductions started to creep into the necessity of the business line. They moved to the PM gear, and it saved a tremendous amount initially. In fact, it saved 430 grams, nearly 1 pound, that was absolutely cut off and fell to the floor around the machinist, just total scrap. That alone was a $3.50 savings in the bronze material. But it was also more than just that cutting conversion. Tremendous savings with machining time. All that scrap was reduced. The production rates were greatly improved. And in this case, the customer had a 75% reduction in the total cost of each and every part of the many, many thousands that were used each year. So that's all nice to say that we can certainly save all of those things, but it goes beyond just being big to create a cost savings. As the slide says, this is a small but mighty with PM. This is a marine industry assembly. It's used to help in the stabilizing of the craft in water while under movement. And this company had been making this, and again, for quite some time. They had been assembling the multi-step gear there in different methods to create a cost-effective solution to their problem. And it did work. This unit's only about 2 inches high, 2 inches in diameter, I'm sorry, and 3 inches high. And as you can see, there's 3 steel shafts that go down through that topmost steel component. That's the only pieces in this assembly that are not powdered metal. We were able to take an assembly that was quite costly and reduce that by producing these gears as an individual part, the 2-piece gear. It also provided cost savings in the assembly by having one source. All things were produced, assembled, and available here. But the biggest savings to them was in strength. We were able to increase the strength dramatically, which allowed them to move to larger and more expensive components for their customer. And essentially to them, there was no cost to go up to those greater results. So it was really just business margin and business opportunity. Now, just the one last thing I'd like to review quickly is cost reduction and VAVE, value added, value engineering. I think a lot of us as customers, a lot of us as suppliers are requested, are looked at to provide VAVE. It is certainly a part of business for all of us. This customer had a very, very well-established business in the marine field also. This device was used to lift boats in and out of the water so that they weren't continuously sitting in the water. It elevated inside the boathouse and just kept the boat a little cleaner, neater, and able to care and condition for it. And again, their product was robust and very well known. What we were able to do is take a look at their margin and create these very large pieces as compact, sintered, and pressed, minus that groove for the ring. So removed totally all of the machining except that ring groove and saved a lot of scrap in doing so. But the other thing we took a look at, and if you take a look closely at that picture we have up there, definitely two different colors. That's by design. The front one was made initially from bronze cast material, all the machining, and we replaced that with bronze likewise. But we were also able to create a lower cost iron version. So by combining both the savings of machine reduction and the savings of that lower cost part, they were able to take on an entirely new line, providing business opportunity that wasn't there prior. So it was really both bottom margin increase and increased share. So our next slide says when. It's all nice to see these things. We certainly offer a team approach to doing this. It's not a one-person thing. We have a very nice, large engineering staff, very large sales staff, very large quality staff. So it's a complement in industrial base to provide that. So these cases that we looked at definitely supported our customers, provided new business, provided new cost-effective solutions to existing business. So I guess the question is, if having looked briefly at this and continuing on with our PM101, we would hope that you see something that you can use in solutions to your market share or to your cost reductions to sort of help your bottom line. Timeline for powder metal is relatively short. In just 12 weeks, we can work to tool up and supply initial parts. Our business model of working with customers that value these items is really key to continuing. I think one last thing that's important before we move on is we are not a high volume part supplier. We definitely have orders from 1,000 and we have parts up to 1 million, but the drive isn't high volume. We are high solution, and that's what we are oriented to doing. Now, while these cases definitely had a sales slant, they are really the hallmark of a PM101. It's providing a net or nearly net shaped part, many levels, many complexities, and doing it with a very high production rate. That's the hallmark of powder metal. If we were to have to start with a blank and do all of the machining, it would be not a cost advantage. It would really be a cost negative. So the things that we've shown you are really the basics of a PM101. We've identified successful areas in which to now move and understand a little deeper the powder metal process. So, what is that? We want to take a look at the PM process in general. We want to take a look at the MPIF standard, and we'll cover what that means here in a few minutes. A little bit of materials, definitely some sintering, and try to grab basic understanding of powdered metal as we move forward in the slide presentations here. So, I think one of the easiest ways is move into a video. We have a very short 3-minute video, and it's just a nice visual introduction into the PM process if you've never seen it happening. And certainly we would welcome everyone to come to our facility, but in this case we're going to take a 3-minute video and really help that push us along into our PM presentation.
Delivering quality products and outstanding service, Symmco has become a distinguished leader in the powder metal industry. Founded in Sykesville, Pennsylvania in 1952, we've dedicated our efforts to provide our customers with the finest quality products that are backed by superior customer and technical services. In our early days, we became known as short-run specialists, and through the years, we've been able to maintain our expertise in this area, as well as excel in long-run capabilities. The PM process has many advantages when compared to traditional manufacturing methods such as casting and machining. Not only does it conserve both raw materials and energy, but it also results in a product that can lead to long-term savings. This is the step-by-step PM process. The part-specific powder is created by mixing the correct amounts of metals and lubricants to produce the physical and mechanical properties of the finished product. During the molding process, the powder is compacted into the desired shape using compressive forces. The part shape is created by compressing the correct blend of materials inside of the part-specific tools. At this stage, the part is considered green and is breakable until sintered. Through the application of heat, sintering permanently bonds the individual metal particles that have been compacted together through the molding stage. This process is instrumental in providing the majority of the mechanical properties of the final product. Sintering temperatures can reach in excess of 2,000 degrees Fahrenheit, depending on the materials. Sizing, sometimes referred to as coining, is the final pressing of the fully sintered part. This process is most often completed on bearings to achieve the final specifications on each individual part, as well as to maintain consistency across the entire lot. Not only does this operation ensure bearing quality, but it qualifies the final part for density, open porosity, and mechanical strength. Under vacuum, the air is drawn out of the interconnecting pores in the part and is replaced by the customer-specific oil. The oil is retained in the bearing's sponge-like inner structure. This process not only prohibits rust, but provides adequate lubrication as the bearing is in use, preventing wear and in many cases eliminating the expense of other lubricating aids. To learn more about powder metal and to see how it can be your cost-effective alternative, contact our sales department. As your one-stop solution, we look forward to assisting you with your powder metal needs.
This next clip, we're going to start with taking a look at the powder metal in the basic system. As you can see, we have a small caricature running that is showing essentially how a powdered metal set of tools works. I'm going to rerun it one more time here, I think, and just to get you just a feel of what's going on. As you can see, that white is the powder going into a cavity, caricature of. The part is produced and ejected inside the same tooling. The bottom tools is what's creating the ejection. The top that you saw coming down is the compaction system. One of the things that we want you to understand as we move forward, and again, caricatures are a little bit deceiving a little bit in how they present, but the powder is held in a column. 100% of the force to create these powdered metal components is in the axial direction. So what you have is a column of powder at roughly a 2-to-1 ratio relative to your end component length. So in this case, 2 inches of powder would essentially create a 1-inch part. And it's also important to note that the tooling is designed to meet your exact part specification, your print specifications, and we combine that exact material to meet the tooling requirements to achieve those sizes. So the tooling is absolutely yours. It meets your component requirements, and it is key to the material that is determined to meet the mechanical properties that would be needed at the end. It's also a quick note here is that the tooling we use is primarily a carbide type die, maybe a carbide pin and very tough tool steel punches. So it's not uncommon to get generally 300,000 or more parts from every tool member. However, it is Symmco's responsibility to maintain those tools for the life of the project. Essentially, in the powder metal tooling, once you've created that tooling to meet your initial specific needs, we must maintain that tool for the life of your project. Tooling costs, let me just get a quick thing out there. Certainly in PM101, we all have that interest in tools. What do they cost? A typical tool to produce a small straight gear is maybe around $5,000. If it's a very complex, large, multi-level gear, it might be up to about a $15,000 expense for that first set of tools. Now we're going to take, before I start, I just want to give you a brief description of what's going to happen is what you're going to see is an actual part being produced. This is live. Absolutely no rate has been changed, so you're actually going to see how long it would take to produce this gear. And it's going to be much more meaningful to fully see the movie. In case you're not going to have audio of the movie itself, that's something we've asked to stop down. What you see is that actual being applied to power by that large box that slides forward. I'm going to let it run one more time. That's about a 4-inch bevel here. So that box is going to slide forward. Filling the capacity created by the tool. The box moves out of the way. That's the top part enters the cavity. Comes back to that part. It's a very tall metal iron. It's very funny. So what I'm really keen on stop, it is a quite repeatable process. That gear is about 4 inches across, about 100 millimeters. After that, it gets that initial compaction force. I want to cover quickly that force. Sorry about that. The force created in that compaction. The way the tools are sitting now, as you can see, there are 4 satellite holes that are used to bolt this unit down. There's one very large central axis bore that creates clearance for a shaft that runs through there. And then the bevel gear turns a common bevel gear that's attached to it. In powdered metal, one of the ways that we calculate how large of a press we need and ultimately how big of a part can we make for you, our customer, is by surface area. It is the single largest surface area, excluding any holes that go the entire way through. So in this case, the 4 bolt holes and the large central hole are not included in tonnage to compact. That part takes right around 300 tons to compact at the density required. And in this case, that is an iron nickel alloy that is subsequently heat treated to create a very hard particle hardness. So the other qualification I'd like to say for length, there is some limit to powdered metal. We would be remiss if we would say that we can make everything. Up to about 3-inch long part is possible. Much over 3 inches, and we begin to lose the mechanical properties that we would think you might need. So again, up to about a 3-inch long part is very doable in powdered metal. Surface area wise, we have up to 750 tons. So we can make a quite large part. An 8-inch gear with some holes up through to reduce some of the weight and surface area is very common. Definitely something that we're doing quite often. And again, the video that we just saw, that very quick character is what we call compaction. And again, at this point, the particles are compacted. We've created that net shape, but it is as commonly called green. it must be moved to a solidification process. And that solidification process is sintering. Sintering, by a very quick definition, is the application of heat to the compact by processing through a powdered metal furnace. It is a heat, the furnace is directly a powdered metal furnace, and it is limited to powder metal. It is a continuous belt system, and it combines temperatures in excess of 2,050 degrees Fahrenheit, that's 2050, or 1120 centigrade, with controlled atmospheres, allowing the part to be at temperature for a significant amount of time to complete the sinter process. So again, very quick description is that continuous belt moves through the furnace as you see it. It is in a furnace for typically about 2.5 hours, and that would account for a gentle cycle going up, maintaining that 2,050 degrees Fahrenheit for a significant time, and then running through a series of coolers that allow the part to come out at a temperature that is not dangerous to the employees in the area. Generally handleable by hand when they come out if you had to. For many parts, sintering is the final process. It does create the mechanical properties in the furnace that are required, and based on the specific needs, however, we can move to associated processes to create a different dynamic. So, primarily all powdered metal parts. Start with powder, tooling, compaction, and sintering. There's really no known parts that we produce without those. But I want to take a minute and look at sintering on a little closer, take a little closer look at sintering. Compaction, running those presses, is a very, very, very mechanical process. The compaction operators are very mechanically minded. Sintering, however, is a very physics-type process. Again, as we said, it goes into that furnace up to about 2,050 degrees Fahrenheit. And one of the keys there is understanding that that temperature is always lower than the melting point of the main constituent. Let me say that one more time real quick. 2,050 degrees Fahrenheit in this case will always be lower than the melting point of the main element in the material. And that is key. We aren't melting the materials together. That would create a system by which you couldn't precisely control the sizes, the specifications. In this case, as you see that small caricature to the left-hand side, it is the energy that moves around every place those particles are connected to create a bond. And then one of the things that I use is if you take your two hands, put your fingers together, the harder you press, the flatter your fingertips become. Those are essentially the bonds that we created in compaction. They are a somewhat elastic, slightly plastic deformation. We don't want to totally break all those particles. Sintering takes the areas at which those particles were touching and bonds them. That heat is strictly energy. Energy moving around those contact points creates a bonding. And it's really key to take a look now over to the bottom right. And what you have there is a scanning electron microscope view of a part that was fractured to confirm it is truly a bonding. That's key. That's integral to us providing a very good part to you, key to us providing the size specifications you need, and key to making sure that it's correctly sintered. One last real quick thing on this slide directly related to the PM101 side is we do have porosity. Compaction densities are typically from, in iron-based materials, around a 6.8 grams per cubic centimeter, up to and maybe as high as 7.3 grams per cubic centimeter. That's quite high in density and typically achieved with some newer technology materials, primarily a warm compaction process where we actually heat the tooling to help us get to that density. Those densities create the higher mechanical properties needed on many of today's components. So density does drive strength, and we're going to take a look at that as we move forward. So where have I gotten us to this point? All powdered metal is compacted and sintered. From there, we can go into a variety of other processes to meet specific demands. It's really common these days to either oil quench, heat treat, austenitic heat treat parts to create a very high hardness. Particle hardnesses at HR60 are easily doable in powder metal. Again, that's a particle hardness of HRC60. That's typical. And we can do that a variety of ways, whether we oil quench. Maybe we need just localized heat treatment to have a high wear area and combine that with a very strong area without brittleness in the drive section. Maybe even it's sinter hardening, which is the newer technology combined with very lean alloys specifically created to create that hardness right in our sinter furnaces, which removes one of the needs for a process operation. While heat treating is common, anytime we can remove that extra high heat and oil quench, it's very likely that we can help drive process variation down. So there are many keys to that technology that helps create a higher demanding product. Now, that's nice to say that we can make parts, that we can do all that, but how do you, in your facilities, your engineering teams, your engineering designers, know how to make and how to use the materials that you'll need to meet that? I think this is the key right here, and this page is only one of many in the Metal Powder Industry Federation standards. This group of powder metal parts producers and powder producers meet to create standards on materials to provide you, the engineers, the mechanical properties that you know you need from your FEA and analysis. Without taking a lot of time, and again on the slides, I'm sorry it's a little hard to see, but this provides us with the exact chemistry of the elements that we would need. That creates a great thing for your quality department to be able to follow along to truly confirm the material meets specifications. And it also creates a couple different methods by which we can confirm strength, transverse rupture strength. There's a yield strength, there's tensile strength, there's compressive yields. So there are ways to identify the material is compliant to the needs of the engineer. It is complex, though. There are many, many materials, and we just briefly talked about oil quench and sinter hardening. It's one of the things that we do try to help you understand. After understanding your needs, how can we best provide the correct chemistry to meet not only the mechanical properties, to meet really cost-effective solutions. It would be nice to always use the most expensive material, the strongest material, but that's just not cost-effective. And so we do definitely assist in choosing those right materials to move the project forward and make sure that we meet those needs. So, materials. And one of the things that leads us to making sure that we do assist you on these is you can see the list is rather complex. There are iron, copper, carbons, iron, coppers, there's ferrous alloys, stainless steels, soft magnetics, sinter hardens, there's bronze, and we've touched briefly on a lot of those. Even within those certain alloys, there's different ways that the manufacturers produce those powders, and they do create certain properties such as compressibility, or a superior hardness, or a superior strength relative to the material and compression. It would be really hard in any PM101 to sit down and totally define all those materials. So in this case, again, one of the things that we as a supplier offer, and as I'm sure others do, that assistance. There is one material, though, I want to touch on that you wouldn't find in that standard briefly. One of the new materials that's really rising in the industry is a soft magnetic composite material, an SMC. and this is the material that you won't find in the standard, but is used in the soft magnetic motor systems to create parts that meet a very high hertz energy input and a very low eddy current demand that the complex motors design would have. So one thing that you won't find in the standards that definitely is available in the industry is those soft magnetic composites. So where have we gotten to? And in the time that we have left, I think it's pretty easy now to say that PM101s don't really happen in a 30-minute window. We hope that this has given you enough information to ask us some questions now to see where I may have confused someone, or maybe just a little more information for those of you who are definitely further along in the powder metal world that we might answer. So what we've done here is we've taken a look at some of the questions, and we will definitely turn this over to Jeff in just a moment, and he will facilitate us in getting those questions and getting those answers. So I do want to take a moment and thank you, and then ask Jeff to go ahead and move to questions so that we can address those things that you might have in your mind at this moment. So Jeff, if you would, thanks.
All right, thank you very much. A few of you have already submitted some questions, so we'll jump right in. However, if you would like to submit a question, just type it into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. Question 1. What advances have you seen in the past 15 years that have improved as far as materials and technology go?
Oh, yeah, good. Thank you, someone. You know, I think that two big things, certainly material, and there are limits. You know, there's only so many elements in this world, and we all realize that. I think the material is coming in at a better sieve ratio, a little cleaner. That's definitely improves how we can make it. There are new lubricants in those powders that allow us to compress to higher densities. The higher the density, the higher the strength. There's really no avoiding that that truth. So driving those higher densities is now available, and it's a warm compaction where we warm the tools and allow that lubricant to be more effective. It also lowers the lubricant. One of the great things about our industry is it can be a very green industry, and we drive to do all of that we can. So lowering those lubricants, using lubricants that are environmentally friendly, are our key to the business that we do here. Pressing technology is the other thing, and I think maybe pressing technology is more important than powder, in that if you have the press that can move the columns of the powder in a much more precise and effective manner, you can create better quality and meet tighter specifications through that. So short answer, definitely powder, definitely those two technologies have increased greatly.
Okay, question 2. Can you provide prototype parts without having to purchase tooling?
Yeah, yeah, an excellent question, and now I see some of the holes in my presentation, so thanks to those who are writing them. We can produce blanks, typically cylindrical type blanks, and from there we can machine the exact specifications out of that blank. And what this provides for you is we would use the exact material that we've concluded is the most robust for the process, and it directly mimics all compaction, sintering, or any post-sintering processes required, in that we're actually checking the exact material and the exact process, and it makes a very smooth transition. There is no tooling required for that. We have some blank tools that we have here that we can create or get those pucks made. And again, we supply the powder, we supply the sintering, so it does meet what you as a customer would see in your component.
Okay. Another question says, when you mentioned HRC 60 hardness, were you referring to macro or micro indentations, and can you explain the difference?
Yeah. Micro, definitely. HRC 60 is a micro. So the difference is between micro and macro. Micro is getting in and looking at the substructure, picking the single most dominant phase in structure and doing a hardness directly on there. Knoop or Vickers type numbers are used to get that hardness. Macro is typically a hardness indentation on the exterior of a part. And really what that's reading is the amount of deflection of that weight into the product. But it is, to be honest, a very viable in-process check. The macro is. We like macro. We do use HRC. Another great standard is HRA. We talked briefly about porosity, and one of the things I like about an HRA hardness is it does exclude some of the variation in numbers that you might see from porosity. So micro does a great job of looking at process intent. Macro does a great job of confirming processes that moves through our production methods.
And does everyone have access to the MPIF standards?
Yes, MPIF standard are available. The Metal Powder Industry Federation is based out of Philadelphia, Pennsylvania. So I'm sure standards are available there. And certainly for our customers, typically we would provide standards as we move forward. So they're a very good resource. And I'd like to say also the standards is quite an interesting book in that we absolutely, in the beginning of the book, tell you exactly how we achieved the mechanical properties, how they were created, what values we used to obtain those. And in the back of the book, there's a lot of good general engineering information from depth of hardness geometry scale to machinability to steam treats and to a lot of different things, and as well as testing dynamics that are used in finite element analysis are in that standard.
And what kind of RC hardness values can you achieve?
Yeah, that's a good question. I think if we look strictly at apparent hardness at this point, because, and I'm going to say micro, one of the previous questions, the difference between the two, micro hardness is a constant regardless of density of the compact, because again, we're looking at the main microstructure. The nice thing about achieving hardness values is they're relative to density as well. So it's typical for a heat-treated part, whether this is by oil quench or by conventional or by sintering, sinter hardening materials. It's very common to be at an HRC 25 up to an HRC 40. That variation isn't part to part. That variation is created by different materials. And again, those are the design features up front that we discuss. If hardness is your primary and mechanical properties aren't really dynamic, we might go to a much lower cost iron copper carbon matrix. If you are looking at a very high hardness and very high mechanical properties, we're probably going to move down into a very high alloy. So those are the things that we work with you on creating, knowing your primary, secondary, and maybe even tertiary design requirements to really get the right powder to meet both hardness and strength.
And what kind of temperatures are required to produce graphite via powder metallurgy?
I think I'm not sure I understand the question, so if someone wants to get back with this later and make sure I understand that. Graphite is used in the powder prior to compaction. Graphite and in the sintering furnace then combines with the iron matrix to form the pearlitic structure, eventually martensitic if we heat treat it. So graphite going into solution with the iron, if that's what the question we're looking at, is in that 1600 degree range, somewhere in there, a little better. Fahrenheit, I apologize, to where we start to put that graphite into solution to combine with the iron to form that pearlitic matrix phase. So if I answered that correctly. Now, in the bronze world, a lot of times we have graphite in the bronze to create a solid solution, and at that point it never really goes into solution and combining any other matrix, so it becomes a graphitic solid state lubricant. So there's two different ways. However, if we've missed that question meaning, please get back with us. Let us follow up and understand that one.
Okay. And can you compare PM materials electrical resistance versus regular materials?
Well, let me say if we're looking at copper-type materials, bronze powdered metal is terrible. I think that's a fair statement. I am not trying to make us look in any worse light, but it's just not a drive. We can produce solid copper components, and I think we're looking at about 89% of what copper would be. So it is inferior to a solid wrought bar copper. We would never want to lead someone into saying that it's as good as others. Now again, that's looking at strictly electrical. I don't think that the question here is leading into soft magnetics in any way. So again, achieving solid copper parts is easy. We can press them. We can what we call size, coin them to specific requirements, but it is inferior to copper, solid copper.
Thanks. And what type of tolerances do you typically require on axial dimensions and diameter or bore dimensions?
Wow, that's a great question. Two answers. First will be somewhat of an avoidance, to be honest. Second is a little bit of, in general, tolerancing. It's hard to say what our tolerances are. Axially, we're controlled by the press, compaction, so there's more variation axial. If you look at perpendicular to direction of compression, typically the outside diameters, the inside diameters, those are controlled by tooling. A little easier to control. There are some materials that are much more stable. So let me say now, if we're talking a whole diameter going through a part that's, let's say, an inch, somewhere in there in length, we're probably going to hold 0.002 to 0.00215 total tolerance, 2.5 thousandths. OD very similar. The larger the diameter, the more tolerance we need, simply because of OD variation or something that way. So let me say, typically in a length, in an axial compaction, we're looking at plus or minus 0.003 up to 0.005 plus or minus. On an outside diameter, we're in the 0.002.5 to 0.003 range, depending on size. The larger the part, the more we would tolerance increase there.
Okay, and then what kind of surface finishes are you able to achieve?
Good question. Just out of the press, if we aren't looking at any kind of post-grinding processes that's necessary, it's really easy to hold a 125 or slightly better. So that's just out of the press. That's an everyday occurrence. Machining, there are some parts that are very, very, very surface finish oriented, and we're in the 32s and below is really easy. Much lower than that if we do need a grinding operation to directly get surface finish.
Okay, and how do we find out more about soft magnetic material properties such as BH curves?
Yep. So what we put up there was a quick slide. I had kept a few slides just in case. The soft magnetics are composite materials. We do definitely have those BH curves. Again, there's a few different materials out there that has different curves depending on the customer's requirements, and we can provide those. It's available. So, but the great thing about that material is it is a 3D flux path material. So all of the parts that you see on there, the larger stator type parts, were all created from powder metal. The largest one we're making now is about 3.5 inch diameter, some very, very small parts also. So it does lend itself very nicely to the entire PM process. It comes as a powder. It is compacted. It has a very different thermal process than typical powder metal. So I don't want anyone to think that soft magnetic sees that same 2050 degrees. Much different animal in the sintering world. We don't truly sinter it. It's a thermal process. And that's what supports that coating on those particles.
Okay, and what are your tolerances for perpendicularity?
Wow. Perpendicularity is really dependent on the size of the product. The larger the surface, the larger the diameter, the more tolerance we're going to ask for if we're talking as pressed and sintered. It's really not uncommon to be looking at a 3,000s to 4,000s perp on a lot of parts. If it's maybe a 4 or 5 inch diameter, we might be in the 0.008 range. Perpendicularity is also something that can be easily addressed with a very, very slight machining, where we would push it up against whatever face was our major datum and take a very slight cut on the board to drive perpendicularity to a face. So there are ways, especially for perpendicularity or a very high flatness requirement, that if we can't achieve it using common sintering furniture, we do a very slight machining process to drive to a tighter tolerance.
Okay. And what is the smallest part that you're able to make?
That's a good question. This is an easy one. We sort of tout our ability. We have a lot of very small iron components that are in sub 1 gram size. So we're talking extremely small. We also have many components that are multiple pounds. So by being in the business as long as we have presses from 5 tons up through to 750 ton presses. So size is not an area that we're afraid to go either big or small on.
Okay, it looks like we have a response from the graphite question.
Oh, great.
Can you produce graphite via the PM process, or are the temperature requirements too high?
That's a good question. Graphite or carbon. There are powder metal companies that produce carbon parts. Unfortunately, we're not one right now, but there are businesses out there that produce carbon parts. So if you want to call in, certainly I would think that our service and sales team would connect up to 1 or 2 that are local, that we might be able to start you down that road if it was strictly a carbon part. So that answers the temperature graphite questions. That helps.
Okay. And is it possible to achieve a bearing race, i.e., say 5210 HRC 60 properties when pressed and sintered with pressed and sintered powder metal?
Yeah, we do have a few parts that hardness, that a wear surface is critical. And again, we can create those HRC 60 particle hardnesses. In this case, high density would be required. We would think we do a couple where they're used in a ball runs in a race. We press the race right into the part, and the balls are then captured inside this part, and they run as a race. So hardnesses are possible with our materials. An HRC 60 particle hardness is achievable. Now, and again, I want to say, and I want to be careful here, at no time should anyone producing powder metal parts say they can exceed the dynamics of a wrought material, regardless of what have you. So we do adequately describe that in that MPIF standard to make sure that you know, while we can achieve those HR60 hardnesses, we don't want to deceive anyone in thinking that we exceed wrought properties. That would be wrong of any powder metal parts supplier.
Okay, and it looks like we have one more question and a few more minutes here. What is the maximum level part that you can press?
Oh, that's a good question. Depending on the tonnage ranges, and again, we have multi-level presses in 60-ton, 150-ton, 200-ton, and 400-ton, where we can make 3 bottoms and 2 tops very easily. We can add a 4th bottom level using maybe a core rod or a die, which is a fixed fill die, common in the industry. So at this point, depending on tonnage, I'm going to say 4 bottoms and at least 2, if not 3 tops, depending on the part complexity.
Okay. Well, that does conclude our presentation for today. I do have to acknowledge we have been told that the audio cut out from one of the videos. We do apologize about that, but you can go on to Symmco's website to catch the full video with the audio. And that will conclude the presentation. On behalf of Machine Design, I'd like to thank Symmco for sponsoring today's event, and of course all of you for joining. Have a productive rest of your day.